So today we would explain regarding the minor losses in piping system, and in that we would take one of the case which is of bend loss. Now when we have a straight pipe, then there would be some frictional losses in it, and that is known as major loss. But the other category of losses is minor loss, which comes due to multiple reasons. Earlier we talked about losses due to sudden expansion and contraction. In the same way, there could be losses if there are different kind of fittings, for example valves, taps, anything like that. And also there are losses whenever we have bends. For example, this is a pipe system and you would see a bend here. Now this kind of bend is known as an easy bend, as opposite to there is another type of bend which is known as a sharp bend. This is 90-degree sharp bend and this is 90-degree easy bend. Now there are different types of losses. In quantity, amount, the losses would be different in magnitude, in sharp bend and easy bend. Now within easy bend, the magnitude of the losses would differ depending on the radius of the bend, provided that the diameter is same. So in this experiment here, we would consider three radiuses. Here in this easy bend, the radius of curvature is 50 millimeter. The second case is here, where we have radius of 100 millimeter, and then there is a third case here where the radius is 150 millimeter. For example, if we want to find the losses here, then as you can see here, what we would do is that we would take two tappings. One tapping is tapping number 13, and the other tapping here would be tapping number, okay, so let's look here. For the 100 mm pipe, we are taking two tappings, 11 and 12. So tapping 11 is here and tapping 12 is here. So whatever difference we would see here would give us overall pressure drop from 11 till 12. Now from 11 till 12, the length of pipe is 0.914 meter. From here till here, it is 91.4 centimeter. Okay. So whatever difference we would see here would be because of the pressure drop from here till here. This pressure drop would be because of two reasons. One would be the frictional loss for this complete length, that is the major loss, and the second would be due to this bend. So let's say if instead of this bend here, this was a straight pipe till here, and because of that straight pipe we would have, let's say, some kind of difference in level here, some kind of pressure drop. Now when we made this bend, this pressure drop would become even more, because we are adding an additional loss due to bend. Now what is the reason for this loss? Why losses happen in bend? Now losses happen in bend due to one of the reason is that there is flow separation. Flow separation occurs across the bend. Flow has some kind of inertia. It wants to go in this direction, but the bend, because of the bend, it has to move its way. So it's a possibility that there would be some kind of flow separation here. Now that depends on how much inertia the fluid is having, and that depends on what is the velocity with which fluid is flowing. That is one reason of losses. And because of separation, there would be a separation zone where there would be some kind of flow circulation, and that causes losses. The other reason is that there is difference in pressure between the outer side and the inner side. Because of this difference of pressure, a secondary flow would occur here. So primary flow is in this direction and at the bend, because of difference in pressure, there would be a secondary flow. Now to maintain that secondary flow, some energy would be extracted from the main flow, and that also causes losses. So these are the reasons for the losses in the bends. Now to perform the experiment, it is similar to sudden contraction and expansion case. This is our volumetric bench, and our volumetric bench is used for supplying flow rate to this pipe flow system. Now to take the readings, what we do is, let's say this is written in liters here. So let's say we are taking till 20 liters, the amount of time which is taken to come to 20 liters. So we would take that time and we would divide the volume, let's say 20 liters, with the time, and that would give us the volume flow rate. Now if we want to change that flow rate, the only thing we need to do is to come here and we can regulate the flow rate using this valve. We can increase and decrease the flow rate. In this way, we would take, let's say, 8 readings of flow rate by changing from the valve. And for these different readings, we would get different values of velocity within the pipe. Now, few of the information which is needed is given here. For example, the diameter of pipe is given to us, the length between the tappings. For all these different radius pipes, 50 millimeter, 100 and 150, it is same, the length between the tappings, it is 0.914. This is the formula which is given, and using this formula we can find out the major losses, and then rest of the calculation and sample calculation and the readings that would be in the later part of the video. In the previous part of the video, we talked about how the experiment would be performed, regarding the experimental procedure and few details. And in the previous part of the video, we were actually at the setup, and that's where we discussed how the experiment is to be performed. Now here what we are going to do is we would talk about how sample calculation would be done and what needs to be done afterwards. So the object of this experiment is to determine head loss due to easy bend. Again, losses due to bends come into the minor loss category. We have major loss and minor loss. Major loss happens due to the frictional effects of the pipe, and minor losses are due to let's say sudden changes in the diameter, certain contraction, certain expansion, or because of joints, because of entrance or exit, or maybe because of different valves being used, and it also may be due to bends. Now there could be easy bend. Easy bend would be something like this, and a sharp bend would be something like this. We have taken 3 easy bends over here, and they have different radius r. We have taken easy bend of radius 50, 100 and 150 millimeters. Now let's say the length is L, and this length is given to us. If we had a pipe, straight pipe of length, same length L, then there would be losses in it, and those losses would be due to major loss, that is due to frictional loss only. But now that we have a bend, and again the length of the pipe is same, so there would be frictional loss, but an additional loss would be due to minor loss due to bend. So that's what we are going to find out. Here you would see the observation table. We are to find the velocity of flow within those pipes. We are trying to find the volumetric flow rate, and for that what we are doing is we would see that how much time it takes
to fill a specified amount of liquid. So let's say for 30 liters, the time which is taken, it is in seconds, so that's given to us. And then x1 and x2 here are the readings of the liquid, and we have taken water as the liquid here in two uh, in the two pipes of U-tube manometer. And then del P by rho G is actually the difference between these two readings. And we have done that for these three bends, that is bend with 100 mm, 150 mm and 50 mm radius. After that, there are a few information which are given to us. At the start of the experiment, diameter of pipe is 13.6 millimeter, length of pipe is 0.914 meter, and kinematic viscosity of water at 30 degrees Celsius is 0.804 into 10 raised to the power minus 6 meter square per second. Now these are the things which are given to us. Now let's start with the sample calculation. Okay. So first of all, we would find the volume flow rate. And that would be the overall volume which we have taken divided by the seconds which it took to fill that volume, and you would get 2.27 times per minus 4 meters square per second. Now to find velocity, we just need to divide this with the diameter, with the area of the pipe. So velocity of flow, by the way, I'm using shorthand. For example, velo for velocity, vol for volume, but to confess, this is not it's not a good habit. Once you are making your report or you are writing your exam, try to write in longhand, don't write in shorthand. It's not a very good way. I can afford it, but since you are being graded, you can't afford that. So a good advice would be to not use shorthand. Velocity of flow in pipe, so that velocity would be, let's say, this Q by A, so 2.27 into 10 power, if I'm taking in millimeters, uh, and then divided by pi by 4 into 10 power 0, 1, that would be in meters, 0.136 square, and that comes out to be 1.57 meter per second. I would highly encourage you to look at my calculations if I have done something wrong. It's a big possibility that while doing calculation I may have miscalculated something, so please look into that. Now next thing what I would do is I would try to find the Reynolds number of flow. Now Reynolds number is a non-dimensional number which tells us a lot about if in a pipe flow we are in laminar regime or in a turbulent regime, and many other things also. So this is something, this number is very important for fluid dynamics study, and you would see how it affects us in unit 4 and then in your third and final year courses also. So RE would be VD by mu, so that would be 1 point, let's say 57 into 0.0136. This is the diameter and viscosity, and this would come out to be 26477, approximately something like that. So this is my Reynolds number. Now the reason I am trying to find this Reynolds number is so that I can find friction factor. So let us say that for the pipe which we have, its surface roughness of pipe, let's say let that be epsilon, is 0.002 millimeter. Let's take it as, and relative roughness, which is the ratio of my surface roughness with the diameter of the pipe, is 1.47 into 10 to the power minus 4. Now, we know that using Colebrook relation, my friction factor which I need, this is small f, this is needed for finding loss due to friction. This formula is 1 minus 1.8 log to the base 10, 6.9 by Re, which is my Reynolds number, plus epsilon by d by 3.7 to the power 1.11. If I would put these values in there, now again these values would be different for different readings. If I would put these values, all of these values, then I would get my small f to be 2.43 into 10 raised to the power minus 2. Okay. Now, if that's the case, then I can find my frictional loss which is also the major loss, and that would be, and due to length L, would be F L V square by 2 GD. Small f's value is provided here, 2.14 into 10 to the power minus 2. Length is given to us 0.914. Velocity for this particular case is also given to us. We also know diameter of the pipe. If we would put all of these values, then we would get something like 0.204. I would highly recommend you to check these values. Now, this overall loss, which is del P by rho G, okay, this del P by rho G, this overall loss would be due to major loss, this HFL, plus the minor loss. Minor loss due to easy bend. That's why this E is there. Now let's take one of the readings. So let's say for easy bend where radius is 50 millimeter, my del P by rho G is given to me as 0.240. Okay, if that's given to me, then if I would plug in this up there, I would get, please look at the units also. I'm here going very fast. I've many a times not written the units, but once you are doing it in the lab, be consistent with the units. Always write your units. Okay, so the units would go here, and check if do you need to put units here or not. How about the units here? Are they supposed to be or not? So please make sure that you check all of that. Okay, so if that's the case, then I can say that my loss of easy bend would be nothing but del P by rho G, overall loss, minus the frictional loss. And for this particular case, it would be 0.24 minus 0.204, and it would be 0.036. So this is my minor loss. And if I know my minor loss, then I can find my bend coefficient also. There's something known as bend coefficient, K, okay, which would be equal to HME into 2G by V square. And how did we got that? That HME is equal to K V square by 2G. Okay, from there we got that. If I would put these values in here, I would get 0.288. I would get something like Okay, so similarly we can find the value of k. So let me call it that this was the k for 50 bend of radius 50. I can find it for other values, for other reading, for all of those readings. Okay, so this would be my sample calculation. Now after my sample calculation I need to make my result table. So let's talk about that. Okay, so what my result table would be. Result table. So let's talk about that. Okay, so serial number, velocity of flow in pipe, that would be different. Choose your units, let's say meter per second. From there I need to find the value of Reynolds number. Then I would find value of my friction coefficient. Now for this pipe, for finding my friction coefficient, my epsilon is not going to change. Epsilon by d, diameter of pipe, again that is not going to change. It's only my Reynolds number which is changing. After that I would find the value of loss due to friction, HFL. Okay, and then afterwards I would find my bend loss, okay, for all of these different radius. Let's say for 50 mm, for 100 mm, for 150 mm. Okay, and once I have found that, actually I would find my bend coefficient. Okay, let's say bend coefficient again for 50 mm, bend coefficient for 100 mm, and my bend coefficient for 150 mm. So this is something which I would find, and after that my result table would be complete. After my result table I need to make my graphs, and let's talk about that now. Graphs to be drawn. Okay, so let's talk about the different graphs which we need to make. Okay. Graphs to be drawn. The first graph would be head loss, that is HM, versus velocity head, that would be V square by 2G. So that would be my first graph. Okay, and I can draw it for all three. R equals to 50, 100 and 150 mm. Second graph would be log of head loss, okay, versus log of velocity. Log of, here V is velocity of flow in pipe. So these are the two graphs which are to be drawn. Now after that we would move on to the discussion which is needed, and let us talk about based on the result table and based on the graphs which we have drawn, what kind of discussion which we need to make. By the way, you can read further regarding this from your book F.M. White or Fox McDonald. In the minor losses, you can read all about bend losses discussion. So the first discussion which we need to do is just like for the sudden contraction and expansion. Discuss the physical significance of the experiment. And when we are talking about physical significance, we don't mean that when the x-axis is increasing, then the y-axis, reading is also increasing. Not like that. But really, what physically you understand, what kind of understanding you got through this whole experiment, what kind of understanding which would help you in field. Let's say, think of it in this way. Second and very important part, show with the help of Buckingham Pi. It's just like we did for sudden expansion contraction. Show with the help of Buckingham Pi theorem the dependence of band coefficient on other factors. And the third point of discussion would be that and this is something which actually you may think about, although we have not done the experiment for sharp bend. We have only done experiment for 3 easy bends, but let us see if you can make certain ideas regarding that or not, that why bend coefficient for easy bend are not equal to the bend coefficient for sharp bend. Okay, you can read in the book also and get some idea about how to do. Okay, that's all for this lab.